So this is our second video in our last unit, and this one really kind of links together with what we were talking about in the last lesson, the idea of the fundamental theorem of calculus. Now, I'm going to get to that a little bit later in topic 3, but essentially the fundamental theorem of calculus said that when you take an antiderivative from, say, a to b, what you're really doing is you're finding the area under the curve from a to b. And so we're going to show you how to do that using calculus. If I kind of already have shown you how to do that using calculus. But today I want to show you a bit more of a, how do I describe this? A more simplistic way of trying to calculate that area before calculus was invented. When Newton and Leibniz came up with calculus, before they would have come up with this method, if you wanted to figure out this area right here, there were some different ways, and a lot of universities or the different classes will show this in different methods. The way that I learned is called Reimann Sums, and basically the idea is that you try to figure out some shapes of these areas right here. For example, this is almost a triangle, right? If you wanted to find the area of that brown in there, it's more or less a triangle. And then what you could do is you could say, well, that's 1/2 of base times height. The base, according to this, looks like it's 2. The height looks like it's 4. So if you do 1/2 of 2 times 4, 2 times 4 is 8. Cut it in half means the area should be 4. Right. Now this, just so you're aware, if you want to kind of test this, this is actually the curve of x squared. Right? And so if you were to differentiate this from 0 to 2, if you were to find the antiderivative of that, it would actually be 1/3 x to the 3. And then if you were to plug 2 and 0 in using the fundamental theorem of calculus, if you plugged in 2, it would give you 2 to the 3rd, which would be 8. And then when you plugged in 0, it wouldn't really matter because 0 would give you 0. So it would give you 8 over 3. Now 8 over 3 is not 4. 8 over 3 is a little bit less than 4, right? If I were to grab a calculator, I'm just throwing it off to the side here. 8 over 3 is actually 2.666 repeating. And you'd say, well, hang on, that doesn't make sense. You just told me the area this was going to be 4, but hopefully you can kind of see, and this is the whole point of my lesson right here, is that there's kind of a section in here where clearly if I made this a triangle, there's some area that I would not have been counting. And so Reimann Sums is a very crude way of solving this. It's not exact. Calculus was able to help exactly solve this issue. But we're going to try to find areas using a different method. And so one of the methods is to use boxes. And what you would end up doing is you'd end up making a whole bunch of little rectangles. Like, for example, on this graph right here, you can see how I'm making like a rectangle here, and here, and here, and here, and here, and here. And if I wanted to find the area, say this is really asking you to find the area from 1 to 4 for the x squared graph. If I wanted to find that, another way of doing it, pre-calculus, would be to, well, let's make a rectangle out of this and out of this. And you can see that if I make rectangles here, it's actually maybe even better than the triangle method. Because if I were to make a triangle, the triangle itself would have even more issues. But by doing the rectangle, I actually cut out a few little gaps right here. Now, I do know that this is going to be over, right? Like if I calculate the area for this curve right now, this area is definitely going to be too big. Right, but if I use not the triangle, but I use the rectangles, hopefully you can see that hopefully my inexactness will be reduced. Now there's actually a couple of different ways of doing this. The graph that I have over here on the left is making a whole bunch of boxes that are slightly too big for the graph. Because if I wanted to find the area of the graph, it really isn't based on boxes at all. Really, it's a smooth curve. Now, I've actually seen some classes where they make them calculate area of these boxes as though it is a four-sided shape, like a trapezoid or something like that. What I'm going to show you, though, is how to work with just rectangles. You can see over here on this right one right here, we're actually going to make some boxes, and these boxes are all going to be too short. They're not enough to account for the area, because really there's some missing area here and here and here. Right. Essentially, the best way that I've learned how to calculate Reimann sums is find the sum of all sorts of rectangles that are a little bit too big, and then you could also find the sum of all the rectangles that are maybe a little bit too small. And here's how you calculate that, and it's got a special notation. It's this symbol right here. This is the Greek symbol for sigma, and really it means the sum of. This is sigma notation. Sigma notation. And it really means like the sum of. So what you need to do is you need to find the sum of all of the rectangles, and your rectangles will have a width and it will have a height. Now the height of the rectangles, you might notice, has a little subscript notation on it. And the reason why that is you'll notice that the width of all these triangles is the same. Here, this width is a half. Here's a width of a half of a half of a half. But the height of all these triangles, well, it really differed depending on which triangle it was. This triangle has way less height than this one, but in terms of width, they all have the same width. But this one has like the third height, this one is the second height, this one is the first height. So you can see in the formula right here, n is actually a little subscript here, letting you know how high it is. Now, the way this notation works is that it's the sum of all of your little of your rectangles, and so it's kind of like a counter. The way this notation works is that 1 is the first one you'll use, and then you'll do for 2, and then you do for 3, and then you do for 4, and then you'll stop with whatever number gets put on the top of this little counter. So I want to show you some more examples of a notation here. Here is that same sort of sigma notation, and there's a really good chance you're going to be shown this at some point in post-secondary. So I thought it was worthwhile to bring it into this section here, just so that you've seen this before. The way this would work is you would start at 1, and then you would stop at 10, and then you would add together all of the possible values you'd have. Now, if it was just this one right here, your answer would be 1, plus 2, plus 3, and you'd keep going all the way until you got plus 9, plus 10. That's how this works. It's 1 plus 2 plus 3, all the way up to 10. Now, this is really similar, but not quite the exact same thing as 10 factorial. If you've done Math 30-1 on this section here, 10 factorial is 10 times 9 times 8 times 7, which involves multiplying. This is a notation that basically says start with the lowest number and keep adding till you get to the top number. Now, on this particular notation right here, the only thing we have is the variable I. But on this one right here, you'll see it's the variable is actually m minus 1. So with the 2 on the bottom, you go 2 minus 1. See how that's right here? Well, then the sum means you need to add to that the next number up from 2. So 3 minus 1. Well, then do 4 minus 1, and 5 minus 1. And then in theory, you could keep going for forever, right? You could go till 6 minus 1, 7 minus 1. So really, this top number here is the upper limit, and this bottom number here is the lower limit as to where to start from. So here's another one. You got m squared. Well, that just means start with 3 squared, then 4 squared, then 5 squared, then 6 squared, then 7 squared. And we stop at 7, because 7 is my top number. And we're adding all these things together. Well, if you kind of get how this notation works, let me go back to this picture right here. What we're going to do is we're going to add the first triangle to the first rectangle to the second rectangle to the third rectangle. And if we add the area of this and the area of this and the area of this, we should be able to come close to the actual area that would be underneath this graph. But the actual area is based on a curved area. So one more thought here. What you may end up actually seeing is rather than it being width times height, it actually might be the width times the function value. And the reason why the function value would exist is that, don't forget, this is a graph of, say, y equals x squared. Well, your height of the graph, right, however high your graph happens to be, however high these boxes are, really that is your y value, right? And your y value can be represented as f of x. So the height of the box will be based on the graph itself, but the width you happen to have, the width is always going to be consistent. And so usually what you have to do is you have to pick a width like a half or 1 or 2 for units. Now that actually leads me really well into my next point, which I'm going to skip ahead to right here. Here's a good example of a picture of how they were able to estimate the area. And you can see that they used a lot of really small boxes. Rather than using a width of really large boxes, the width of all of these looks like it might be like 0.1. Right, you can see right here that up to right here is 0.5. So that means up to here is 0.1, this would be 0.2, 0.3, 0.4, 0.5. So the width in all of these cases would be 0.5. And the height in all of these cases is really f of x. Right, depending on where you happen to be. The height right here is based on the graph you have. The height right here is based on the graph you have. And you can see that the way this one works out is by using really small, narrow width for boxes, that there's going to be a little bit of excess right there. Do you see how there's a little bit over the edge? There's a little bit over the edge right there as well. There's a little bit too much right there. But if I circle in a different color, you might notice, well, hang on, right about here and here and here, you're actually kind of missing a little bit. There's a little bit of an overage right here, but there's a little bit of an underage right next to it there. Well, really, in theory, that should almost average out to not really being all that much of an issue. And you can see that actually the estimated area based on these Reimann boxes was 0.187. The actual area is 1.193. That's not bad. Right? So again, this is a very crude method. It's nowhere near as exact as when Leibniz and Newton eventually discovered how to be able to use calculus to solve this problem, but it's not a bad method. Right? Here's another picture to kind of illustrate the same sort of concepts here. What you could do is you could use rectangles and find rectangles that are all a little bit too big. And you can see that right here, this rectangle I made is too big, and this one right here is too big, and this one's too big. And I can tell that because like there's some excess area that's a little bit too much. Right? Well, one way that you could combat that is you could also then find all of the rectangles that are a little bit too small. And so what ends up happening here is rather than putting this corner here on, like, see how this corner here is on the right side of the rectangle? We would call this a right-bound triangle. Well, here I made a triangle. This is the exact same triangle. This one is really this one right here. Only now the height I actually put on the opposite side. And so I could measure the height from the right-hand side of the rectangle, or I could measure the height from the left-hand side of the rectangle. And you notice that all of these triangles right here, they're a little bit too small. Right here, you're missing some area, and you're missing some area, right? Where we're counting not enough. Well, what I'm going to show you guys to do is a good way of trying to estimate just how much area there would be is let's find the left-hand bound, let's find the right-hand bound, and let's average them. Let's divide them by 2, and that should be pretty close. Before I go too far, I do want to come back to this slide here. I skipped one here just to make sure you guys get the concept. 2n, well, the counter just means make it 2 times 1, then 2 times 2, all the way up till 2 times 6. And then one thing that these slides aren't doing here is you actually do have to add all these together to get a final number. Right? In our example here, this will be then the area under a curve. Sorry, my writing's really poor there. So, I mean, here's essentially what that notation means then, is this is find the area of the first box, find the area of the second box, find the area of the third box, find the area of the fourth box, and finally stop when you've decided to stop having boxes, which really depends on what number goes on the top. So, okay, here's another example of some pictures to describe this concept. Again, you can see that if I use really wide boxes right here, so I only used 4 boxes right here, there is a huge amount of overage right here. Then we're actually missing some right here. And there's a little gap right there that never gets covered. Here there's too much. Here there's too much, right? Like there's huge problems everywhere. Whereas if you were to use really narrow boxes, really small widths, you see that like the approximation, that's a really good word to use here, by the way. These are known as approximations. The approximation, I-O-N-S, the approximations are actually not bad, all things considered. But it depends on whether or not you use a width that's small or big. Right? Now, you can still tell on this one right here that there's a little bit too much. There's a little bit too much right there. But then right here, there's a little bit too much. I think you can see right there, there's actually a couple of gaps sitting in there. So that's why when I teach this, I like to show kids to average. But you may see this notation at some point as well. This notation basically means that you're going to have a width and a function, and you're going to do it infinitely. You're going to have an infinite number of small, little, tiny little boxes. And if you could do that, that would get you your area very precisely. That'd be the hope. So anyways, let me show you how to do this sort of question now. I've talked a lot about the theory. Really, the important thing now is just, can you do this? So what we'd like to do is find the area under the graph of y equals 2x squared plus 1. Now, first I'm going to cheat, and really quickly I'm going to find it using calculus. If you know what this graph looks like, this graph is a quadratic graph that looks something like this. And if we want to find the area from 2 until 6, let's say this would be 2, and let's say that right about here that could be 6. Okay? Okay, so if 2 and 6 are going to be here and here, then we're really looking for this area along here, which, again, can't really be approximated very well using a triangle. Like I could. For example, if I zoomed in really close, it would look something like this, and there. This would be 2. This would be 6. And so, I mean, original ideas would be, well, we can make a box like this, and we can make a triangle like that. And then we know that if we find the area of the box, it should be length times width. And you find the area of the triangle, 1/2 of length width, that we know that would be too much. So sometimes what they suggest is, well, let's just use rectangles instead, and we'll average the upper and lower bound rectangles. So now I did say I wanted to use calculus first to know what our answer was going to be. I'm going to kind of cheat. This is really next day's lesson anyways, but honestly, these two lessons need to go together. So I mean, here's how we'd calculate this using calculus. Newton and Leibniz discovered that if you just find the antiderivative from 2 to 6, fundamental theorem of calculus, essentially, for this actually gives you the exact value for how much area there is between the axis, by the way. It's the axis that you go between and the curve itself. So to antiderive this would give you 2x to the 3 over 3 plus x. And you'd be finding that from 6 to 2. So then the last thing you need to do is you'd plug in 2 times 6 to the 3 over 3 plus 6. And then you'd be subtracting the lower bound value, which is 2 times 2 to the power of 3 over 3 plus 2. We just need to solve for what that happens to be now. So 2 times 6 to the power of 3 divided by 3 is 144. Add that to 6, that would give me 150. Then I have to subtract 2 times 2 to the power of 3, which is 32, divided by 3. This one here is 10.6 repeating, plus 2, so that's 12.6 repeating. So 150 minus 12.6 repeating gives me an area, which by the time I'm done should be 137.3 repeating. So I just solved that using the fundamental theorem of calculus, which honestly, like I said, this is what I'm going to show you in the next video, but I'm just kind of jumping ahead now. So I want to erase all of that except for the 137.3, and hopefully we'll get the same number again. What I'd like to do now is approximate this in a pre-calculus setting using Reimann sums, and we're going to do 6 Reimann sums. So I'm going to redraw this again here. I'm just going to draw just a really big curve here. So really what we need to do is start where we're at 2 and end with where we're at 6. And to do this, we're going to draw a bunch of rectangles. And I'm going to use the little rectangle drawing tool that I think I can do with shapes here. Where's the shape of the thing here? There it is, shapes, a rectangle. And so I'm just going to copy and paste here. Here's a rectangle. Now this is obviously too tall, so I'm going to have to, can I shrink its size? Oh, maybe I can't do this the way I want it to. I want to like make it less tall. Okay, apparently the rectangle tool is not going to work. Let me try one more thing here. Because this is a square. No, I can't change its size. Rectangle. But once it's made, I can't change it. Okay, well, I guess I'll have to do it like this. So here, I'm going to make a rectangle that's going to be a little bit too big. And I'm going to do another one and see how this is a little bit too big. And there's another one that's like a little bit too big. Now, the problem I've made right here, though, you can see is that I've lined up my my right-hand side with these edges right here. And first off, the problem then is that these widths right here are not the same. So I have to try to make the width be consistent. So I may just have to freehand draw them. Now I want to have 6 Reimann sums from 2 to 6. So I'm going to go from 2 to 2.5 to 3 to 3.5 to 4. Maybe I should change that. Let's make it 8 Reimann sums, just because then I can go up by halves. So let's try this again here. Let's go to 2 to 2.5 to 3 to 3.5 to 4 to 4.5 to 5. Just going to keep this going to 5.5 and then 6. Okay. And by averaging these Reimann sums here, I need to make some boxes. So let me see if I can try to make these boxes here. First, I'm going to make boxes that are all a little bit too small. So I'm going to start over here in black so you can kind of see them. In black, here is a box that is lined up with the function right there at the 5.5 mark, and it is going to be a little bit too small for what we're looking for. And then here's another one right there, which is lined up on the left-hand side with the 5, and again, it is a little bit too small because there's a missing piece right there. I'll do the same thing here. This is a little bit too small. This one's going to be a little bit too small. This one here is going to be too small. This one here is going to be too small. This one here is going to be too small. And that one there is going to be too small. So I'm going to recognize that the answer I get from finding all these boxes is going to be too small compared to what the true answer is going to be. But that's okay, because I'm then going to find the answer from the, these are all of the left-hand bound boxes. Then I'm going to find all the right-hand bound boxes. So let me kind of write this out here. Here's my left-hand bound boxes. And the way that I'm going to find these areas is that it's going to be the sum of the width times really the function, because that really is the height. This is your height. So how do I find the width? Well, the width, I made it 0.5. I kind of arbitrarily chose to make it a 0.5, and now I have 8 boxes to average. Not 6, but 8 boxes. So I really need to do 0.5, and then I need to times by how high the boxes are. Well, the height of each of these boxes is really based on the graph y equals 2x squared plus 1. Because this height right here, well, the height of this box that I just solved here is when I plug a 2 in right there. So what I really need to do is do 2 squared plus 1. I'm going to need to erase this. Okay, that was 137.3. Let's not forget that. But then I also need to do the next box. Well, the next box also has a width of 0.5, but now its height is by 2.5 squared plus 1. That's this box right here. See how right there the height of this box is at 2.5 for an x value, which means its y value is all of this. I should put those in an extra bracket, actually. So this is box, I'll even label them. This is box 1, box 2, box 3, box 4, box 5, box 6, box 7, and box 8. So this is box 1. This is box 2. All right, so keep the pattern going. Box 3, its width again is 0.5. What is its height? Well, its height is, well, this box right here, its height is based on this corner right here. And this corner is where you have an x value of 3. So I'll go 2 times 3 squared plus 1. Well, once you get the idea, just keep this pattern going. So we wanted to have, we said 5, that's 5, 6, 7, 8. We said we wanted to have 8 boxes. All right, so keep going, 0.5, 0.5. They all have a width of 0.5. Now, all of their heights, well, their heights just keep increasing by that next incremental x value. So my next x value will be 3.5. Then the next one after that will be 4. The next one after that will be 4.5. The next one after that will be 5. And then the 8th one will have a height of 5.5. And let's just recap right here. That 8th box, yeah, look, the 8th box, this side stops at 6. But where the box was based off of was a height of 5.5, which is why I'm going to expect my answer to be too low, because there's missing area from here, and here, and here, and here, and here. We've got missing area. So even though I believe the correct answer is 137.3, I'm going to expect this answer to be more like 120 maybe, because this is definitely too low. So now I'm going to grab my calculator, and I'm just going to do this one by myself. You guys will have to just confirm. Probably pause the video for a second here. Just make sure that you have the same thing that I do. So it's 5.5 squared plus 1. So I'm going to grab my calculator. I'm going to find all these different values here. So I found the first one here as 4.5. And now what I'm going to do is I'm actually just going to pause, and I'm just going to fill them all in, and then you guys can do the same thing. Just make sure you get the same values as me. Okay, so I just took a few minutes here to find what all of these values were, and hopefully you just paused the video and did the same. Now, this is what makes Reimann sums not very efficient, is that I can solve this using calculus in seconds, whereas by finding all these boxes, this is very tedious. I've now found 8 boxes, all of which I know are too small, and now what I have to do is I have to sum them up, which is basically where this notation comes from. We're going to take the sum of the first box to the 8th box, and we're going to do the width times the f of x value for whichever box we're looking for. So the width was always 0.5, and then the f of x value really depended on which box we were working in. And so we basically have to add up these 8 boxes. So last thing to do is let's add all these boxes to each other. So 4.5 plus 6.75 plus 9.5 plus 12.75 plus 16.5 plus 20.75 plus 25.5 plus 30.75 gave me a final answer of 127, which is about what I expected, because I know the correct answer to be 137. Again, I'm getting ahead of myself. We haven't actually learned necessarily how this works all that much. We just know that it works. But all of these boxes in black here, they were too small. And so 127 actually makes a lot of sense. Now, different teachers will teach Reimann sums differently. Okay, there's no one right way of doing this. So you're going to want to make sure you ask whenever you get to this section. Some teachers teach boxes. Some teach to use trapezoids or different shapes, and you add up different shapes. But at the end of the day, it usually involves the sum of very, very, very small boxes. I like to average Reimann sums because I recognize that we just used boxes that were all a little bit too small. Now I'm going to redo the exact same exercise, and I'm going to find boxes that are too big. And so in purple, I'm now going to make boxes that are now based on the right-hand side. See how right up here, my right-hand side, I'm now going to base it on? Right here, I'm going to make a box where the right hand is where it stops. And now if you can see how these boxes are going to get made, all of these boxes are now going to be too big. Clearly, right? Now they're all too big. But ideally what should happen is the amount of overage from the right-hand boxes should be about the same as the amount that it's under from the other box. So what we have to do now is in purple, I have to refine the sum of all of these boxes, and it changes now. Because, for example, this box number 1 is now actually not, I know it's kind of hard to see because it's zoomed out, but this box number 1 is actually not based on the 2 value, it's based on the 2.5 value. And this one right here is not based on the 2.5 value, it's based on the 3 value. In fact, what you might actually discover is that many of these boxes are the same as each other. Black box 2 is the same as purple box 1. Even right here, black box number 6 is purple box number 5. So really all I need to do now is take the exact same work I did right here, and in purple, this is now purple box number 1. This is purple box number 2. This is purple box 3, 4, 5, 6, and 7. And if I go back up here, black box number 8 was a little bit too small right here, but purple box number 7 is the exact same box as it, only shifted over 1. What I really need is one more box. So this is actually purple box 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8. I just need to find purple box 8. And you know what's weird about purple box number 8 is that it's the exact same thing. It's 0.5, but now it's the last number that I didn't use. You know how I was supposed to go from 2 till 6? But right here I had to stop at 5.5. Well, now I'm finally using that 6 value there. So I know it's a little bit messy here, but let me do the exact same thing one more time. Plug in 6 now. That box is too big at 36.5. But now when I sum these boxes, I'm actually not using the first box. I'm actually using these ones right here. These are all the boxes that are a bit too big, whereas right here, these were all the boxes that were going to be a little bit too small. So what I'm going to do is I'm going to go back and I'm going to re-average all of those numbers I have right there, except I'm not going to use 4.5, and in its place I'm going to use 36.5. And when I do that, I get a number that I know to be too big. I get an average of 159, which means that the purple boxes have a sum of 159. That's too big. The black boxes had a sum of 127, but I'm hoping that the average between the two is actually going to be roughly what we're looking for. So I'm going to take 159, I'm going to add 127, and then I'm going to divide by 2. And I am getting 143. Now, that's not bad. It's pretty close. It's not quite 137.3, but it ends up being more or less what I'm looking for as the average, right? And if you can kind of see that concept again right here. Here, if I use boxes on one side, and then I shift those exact same boxes over one, this will have maybe a little bit under, this will have a little bit over. Ideally, the amount that's excess right here should be the amount that's over right here. And by summing these should be pretty close. Okay, that's essentially the concept. Well, once you get the idea, it's basically the exact same thing over and over again. So I want to try one more example with you. I'm going to go a little bit faster, and then you guys should hop right into the next video, because the next video is all about, well, let's stop using Reimann sums. Let's actually use calculus to find this now that we've discovered a shorter way. But I will ask you to do Reimann sums, and you're probably going to get asked this in university. You have to know how they want you to do it. They might want you to average right-hand sides or left-hand sides. They might want you to use trapezoids. They might want you to find an average. But the basic concept is add up a whole bunch of small boxes. So again, what we're going to do right here is we're going to find a value from 1 till 6. And in between, we're going to have a whole bunch of boxes, right? So just to make sure it's clear, I'm going to use, rather than drawing in all of the boxes, I'm just going to draw in, like, say, 3 boxes. Here I'm going to draw a box that's clearly too small, clearly too small, clearly too small, and clearly too small. Those will be where the left-hand side touches. So those are your left-hand boxes. Then I'm going to draw the exact same boxes, only now I'm going to draw them too big. See how that one's too big? This is too big now. This is too big. This is too big. Now the purple boxes are almost identical to the red boxes. Really, this red one is that purple one. This red one is that purple one. This red one is that purple one. So almost all of the boxes are the same, except I have one purple box, which is too big, and I have one red box, which is too small. And those are the ones that only get used once. Otherwise, a lot of these values get used more than once. So once I get that concept, here's how I show my work. First, I just got to figure out what width we're going with. And I believe the width, if we're going from 1 to 6, well, that's 5 units in between, right? But if I want 10 boxes, that means, again, they're all going to be a half. So I always go with a half unit. So what we need to do is to find the sum of our width times our f of x values. It would look like this. 0.5 is my width. And I'm going to times by my x value. So I'll go with 1 squared minus 4. There, that should give me my first box. Then we're going to do 0.5, and I'm going to go up to 1.5 squared minus 4. And I'm just going to make a big table here. So again, I'm just going to pause for a second here and make the table, and then you guys can do the same thing while I pause. Okay, so I took some time and I wrote out all of the different possible boxes. I'm going to have, that's a physics test. I've got a 1 squared minus 4, a 1.5 squared, a 2, a 2.5, a 3, a 3.5, a 4, a 4.5, a 5, a 5.5, and a 6. And if you count them up, by the way, you'll notice that I actually have 11. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which may seem odd, but keep in mind that the first one through the 10th ones are going to be all the boxes that are probably too small. And then the second one through 11th ones are all the ones that are too big. Right? And so if I find the average of purple and red, that should be pretty close. So again, I'm going to actually pause for a second. I'm going to find what all these values are. And then you can compare to mine as well. So sometimes I'll tell my kids, like, this is not hard work. It's actually very simple. You're just plugging in 0.5, typically. Maybe your width could be 0.25 or 0.1 or 7, but usually it works better when you use a smaller width. And you're just multiplying by a y value that goes up by a certain amount every time. As those y values go up by a certain amount, you get different areas, and you just average those. It's not hard work, but it's very tedious. So I'm going to pause again so that I can find some of these values, and then you can compare. Okay, so I calculated all these values. Again, this just took me a couple of minutes to do, so hopefully you pause the video and do the exact same thing, or you could just take my word for it. Here's what happened. I got a negative area and a negative area, which kind of makes sense, actually, because when you think of this graph right here, the reason why you're going to have a negative area is that this quadratic is down here below the axis, which means that some of these boxes that you're working with, they're actually on the negative side of the line, because then eventually it becomes on the positive side up here later, right? You know how the intercept for x squared minus 4 is going to be at 2? The first couple of boxes you work with will have what's considered a negative area because they go below the axis. Below the axis makes it negative. So anyways, now that I found all these values for my 11 boxes, and I got to make a point here. If I ask you to actually average 10 Reimann sums, I'm really asking you to find 11, because we're now going to take the first 10, add them up, take the second 10, add them up, and then divide by 2. So this one I will just do I won't pause this. So I've got negative 1.5 minus 0.875 plus 0 plus 1.125 plus 2.5 plus 4.125 plus 6.8.125 plus 10.5 plus 13.125. Okay, and that's where I stop. So I'm going to stop at the 13.125, and I'm going to get one average. I'll write it as, like, say, capital SN being 43.125. But then little sn involves the exact same average, but instead I'm not going to use this one, and I am going to use the last one. So I just reuse the exact same list, and I just go in my calculator, I re-pull the last one up, and all I do is I pull off the negative 1.5, and in its place, I'll just add the 16 to it. And in this case, I got 60.625. Now, right off the bat, this makes sense. These are boxes that are all too big. These are all the ones that are too small. So if I add them together and divide by 2 and find an average, this is considered a Reimann sum. So I have an average of 51.875. And this is I can't stress this enough. This is an approximation, okay? If you wanted to do this for real, we would never do this because calculus has now found a better way for us. And so that's what I want to finish this last lesson with, which kind of leads into the next one. Newton discovered, using his calculus method, that if you derive or antiderive x squared minus 4 from 1 to 6, this will do it exactly. So you know how I just calculated it's about 52? Well, if you find x to the 3 over 3 minus 4x, and you do that from 6 to 1, this should give you the same answer. So we want 6 cubed over 3 minus 4 times 6, and then subtract 1 cubed over 3 minus 4 times 1. Let's see, what does that give us? So 6 cubed over 3 gives me 72. That'll be minus 24. There'll be a plus 4 right there, and then you'll have to subtract a third. Right, minus 24, double subtract means add, minus a third. All right, so let's put that all together. 72 minus 24 minus a third plus 4 gives me, using calculus, 51.6 repeating. Well, right here I got 51.875. Reimann sums did an excellent job of getting us an approximation, but 51.6 is what we're going to work on from now on as being, let's use calculus to find the exact value. But using this approximation, again, of picking boxes, if you just did a whole bunch of rectangles, it should be pretty darn close. It's better if you average over and under It also works really well if you use trapezoids, and I've seen that being asked as well. So pretty much every university course will ask you to do some sort of Riemann-type sums. At the end of the day, what you need to know is that a Riemann sum really involves the sum of very, very, very small shapes. And then if the width is small, like say 0.5 or 0.1, it works better, which is why you may see some formula like this at some point right here. The limit as n approaches infinity, so you want to have an infinite number of really small widths. Your widths want to be like infinitesimally tiny, like from here to here apart. So tiny that you can't even see the difference. That would actually be very, very exact. So, okay, one last thought, and then I'll stop this video here. I'm gonna ask you to do a couple of Riemann sums, one on your final exam and one on your assignment. But this is not a very common thing to do. This is more of a lead-in to the fundamental theorem of calculus being used in our next topic, which is area under a curve using integration. But the good news is when I do this next video here, we should already kind of know the basics of this. So anyways, I don't expect you to do this a lot because it's a lot of writing out small little details, but know how to do it once or twice. So, okay, I'll stop this there.